Yeah, today topic is optical isomerism. See, isomerism classification is this one. Isomerism is mainly two types, structural and stereo. In the structural below five types we discussed in the structural isomerism. The stereo isomerism is two types, configurational and conformational. The configurational again two types, geometrical and optical. In the last video we discussed geometrical isomerism. Now the topic is optical isomerism. This geometrical and optical is raised due to CC bond restricted rotation. Means there is no rotation in between carbon and carbon bond. Now conformational is due to CC bond rotation. We will discuss later. See here, optical isomerism, certain substances possess the property to rotate the plane of polarized light. Such substances are called optically active substances, and this phenomenon is known as optical activity. What is that? Some substances are rotating plane polarized light. Now, what is that plane polarized light? In this topic, you will learn these points. One is ordinary light, monochromatic light, plane polarized light, and asymmetric carbon. These four things you will learn in this topic, right? First, ordinary light. This is ordinary light you can see anywhere. So it's an electric bulb and Vibgyor colors. Means different colors, different wavelengths. It is giving. So the light which has different wavelength and vibrate in all planes perpendicular to the direction of the propagation is called ordinary light. Okay, just away this one idea is enough regarding this. There is no important here the definition. Monochromatic light. Monochromatic light may only a single wavelength vibrating in all planes perpendicular to the direction of propagation is called monochromatic light. Here only one color is present. That is only very simple. Monochromatic light means only one color. Next, plain polarized light. Plain polarized means that is only normal light. When a monochromatic light is allowed to pass through a nickel prism, when a monochromatic light is allowed to pass through a nickel prism, the transmitted light contains vibration in only one plane. Such light is called plane polarized light. See here, in all direction it is a randomly oriented light, but when it is passing through this polarizing filter, it is all different directions are filtered. Only one direction light is allowing through this filter. Okay, only one direction light is there. So next, you can see here asymmetric carbon. The fourth point is asymmetric carbon means the carbon which is attached to four different substances. The carbon which is attached to four different substances. See, OH, methyl, H, COOH. All four different. The carbon atom which is attached to four different monovalent atoms or groups of atoms is called asymmetric carbon atoms. It is indicated as C star. Okay, all four different groups it should be. Next, optical activity. Optical activity when plain polarized light is passed when plain polarized light is passed through the aqueous solution of a substance containing a symmetric carbon atom, such as it is observed that the plane polarized light is rotated either to right or to the left. This is called optical activity, and the substance is said to be optically active. Understood? No. Once again you read it and I will show you the figure, then only you can understand clearly. See here, this light is there. This light, while passing through this aqueous solution, which is containing a chiral carbon, the carbon which is attached to all four different groups. Okay, this substance is there. So this light, vertical, exactly vertical is there. This light is, while moving through this solution, it is rotated little bit. Okay, suppose initially like this is there straight, so to this 90 degrees exactly, now little bit rotated, so this phenomenon is known as optically active. Okay, you can read once again. Now when a plane polarized light When a plane polarized light is passed through the aqueous solution of a substance containing asymmetric carbon, such as it is observed that the plane polarized light is rotated either right side or left side. Okay, this is called optically active. Now I think it's understood clearly. This is the one polarimeter. The solution is there. Here the light is entering through this slit. After entering in this, it may be rotate little bit, so it is coming like this with some angle. So this solution is rotated. This solution rotating this light. So this solution is called optically active solution. Optically active solution. Right? Optically active solution. So example, lactic acid, 2-chlorobutane, glucose. These are the examples. So this is the rotation. Vertical line is there. While moving through the solution, it is rotated. So direction of propagation. So the optically active organic compound which can rotate the plane of polarized light to right is known as dextrorotatory compound. If it is rotated anti-clockwise, that is levorotatory. Okay, this dextrorotatory is denoted by D and plus sign, D and plus sign, small d and plus symbol. See here, D lactic acid, that means this lactic acid rotating light in the clockwise direction. Next, if it is rotating anti-clockwise, that is called levorotatory. The symbol is minus sign, right? Levorotatory minus sign. The symbol is minus sign, as well L we are taking. Here we are taking minus sign and L. So D means plus, L means minus, as well D means clockwise rotation, L means anti-clockwise rotation. So these are the symbols. So if optically active compounds, two compounds are there, the resultant optical activity, it may be cancelled if it is opposite direction. If those are in opposite direction, the resultant rotation, it may be cancelled. It will be cancelled compulsory. See now, optical isomerism. The different atoms of optically active compounds having same molecular formula and structural formula but having non-superimposable object and mirror image relationship and opposite action on plane polarized light are called optical isomers, and the phenomenon is called optical isomerism. What is the thing here? Different atoms of an optically active compound having same molecular formula. Isomer means same molecular formula. So up to this clear? Isomer means same molecular formula. And here stereochemistry means the stereo isomerism, the structure also same. Okay, structure also same. But where, what is the different? Three-dimensional arrangement is different. But having non-superimposable, now, especially in optical isomerism, these two isomers are mirror images. These two isomers are mirror images. See, mirror images means suppose here A and B is there, C, D is there. So this mirror, so here it will be A, this will be B, upper C, down D. These are the mirror images. See, same molecular formula and structural formula, but having non-superimposable object and mirror image relationship. ये दोनों का mirror image relationship है. Non-superimposable means if you take this image, this is the image suppose. If you take it, this image, put on the original one, if it comes C below C, A below A, D के नीचे D आगे तो those are superimposable. Those are called superimposable. So for isomerism, for this optically active compounds, those should not be aligned. Those should not be aligned. That means A के नीचे A, B के नीचे B नहीं होना चाहिए. Then only optical isomerism is possible. If it is aligned, aligned means A के नीचे A, C के नीचे C आ गए तो those are not exhibiting optical activity. Those are not exhibit optical activity. Now see here some examples. Van 't Hoff and label theory. It states that four valencies of carbon atom do not lie in one plane, but they are directed in the four corners of a regular tetrahedron with carbon atom at the center. Okay, we know that methane is the tetrahedral geometry. So three-dimensionally those are arranging in the tetrahedral manner. Next, the light of single wavelength vibrating in all planes perpendicular to the direction propagation called monochromatic light. Which of the following are optically active substances? Lactic acid, 2-chlorobutane, glucose, all of these. So how we know these? We have to know the structure, then only we can do it. Next, the stereoisomers which are not mirror images of each other are called diastereomers. If it is mirror image, then those are called enantiomers. Enantiomers and diastereomers. Okay. Now see some more details. So optical activity. So this is the normal light when we passing this through this Nicol prism. Only monochromatic light is there. This light, while passing through the solution, it may get rotated either clockwise or anti-clockwise. Yes, next. To calculate this, this is the formula. This is the formula here. Alpha, D and T. Specific rotation determined at T degree Celsius using D line of sodium light. Here light we are taking a specific light, okay, then only these values are not changing. T and D always constant. So what is the changing here? Obviously alpha observation, that light rotation is changing with the solution. See, initially it was like this. It is initially after emitting, the light is bending like this. So this much is the theta in between these two. So this is the alpha theta, that means alpha observation. In some books it is written as theta also, observation. Next, specific rotation determined at, it's okay. Next, what is L? L is the length of solution in decimeter. Here we are taking one polarimeter, so that is in generally 10 centimeter, that means 1 decimeter is there, but if it is not there, you have to convert into decimeter, you can take that value, right? Next, C. Here C is the concentration of the active compound in grams per milliliter. Grams per milliliter. Next, that numerical is not much important. Now, asymmetric carbon, clear. Asymmetric carbon or chiral carbon, the carbon which is attached to 4 different groups. All 4 bonds of carbon are satisfied by 4 different atoms or groups. It is chiral. Chiral carbon is designated by an asterisk. Optical isomerism in bromochloroiodomethane. So this is the chiral carbon. Next, the molecule has one chiral carbon as designated by star. Thus, so molecule is chiral. It is non-superimposable on its mirror images. Suppose if you take इसका mirror images, chlorine, hydrogen, bromine and iodine, if you put it on this original, it never align. So that means non-superimposable. Only one chiral carbon is there, that is always non-superimposable. Non-superimposable means obviously optically active. Optically active. Right. So according to Van 't rule, the number of optical isomers should be equal to 2 to the power of n. 2 to the power of n. What is it to n here? N is the number of chiral center. N is the number of chiral center. The Fisher projection of the two isomers are given like this. Now, here these two are there. This first one and second one, these mirror images, these are called enantiomers. Enantiomers, right? Enantiomer means the mirror images which are not superimposable. Those are called enantiomers. If those enantiomers together, if it is present, that mixture is called racemic mixture. Racemic mixture. What is a racemic mixture? Enantiomers. If enantiomers are together are there, then that is racemic mixture. So racemic mixture optically inactive. Racemic mixture is there, optically inactive. Optically inactive. Why optically inactive? Individually both are optically active, but as a racemic mixture, this is optically inactive because one compound is rotating clockwise, the other compound is rotating anti-clockwise, the resultant becomes zero, so optically inactive. It is a plus isomer, it is a minus clockwise rotation and anti-clockwise rotation, resultant is zero. So this phenomenon is known as external compensation. Due to external compensation, racemic mixture optical activity is zero. Due to external compensation means one compound rotating clockwise, the other compound rotating anti-clockwise, dono getting cancellation. Next, molecular formula is same for enantiomers, structural formula same, stereochemical formula is different. Stereochemical formula means 3D, 3D structure, that is a different. Physical properties, melting point, boiling point, density, solubility, these all are same except plane polarizing light. Okay, except ppl, remaining all are same. Chemical properties with optically active compounds, with optically inactive compounds same, with optically active compound it is different. Optically active compound it is different. Why? See one example. I am taking one optically active plus compound. It is reacting with X. So that is plus and X is combined. Plus X is combined like this. Done. Now in case of plus, it is a positive deviation, means clockwise rotation is there. It is reacting with positive and negative, means these are optically active compounds. If one optically active compound, if it is react with one more optical active compounds, here it is giving plus plus, here it is giving plus minus. So these two are different products. These two are different. That's why optically active compound with optically active compound reactivity is, chemical reactivity is different, but optically inactive compound के साथ reaction same. Inactive के साथ same होता है, active के साथ different होता है, right? Optical isomerism in compounds having more than one chiral carbons. More than one chiral carbons. So here we have to know this plane of symmetry and center of symmetry, n-fold alternative axis of symmetry. If these symmetries are absent, then the compound, then the compound will be optically active, right? If any one of the symmetry is present, then optically inactive. Okay, see here, these two are mirror images, mirror plane is there, 1 and 2, above 1 and below 1 are mirror image, hence plane of symmetry is present, therefore optically inactive. Optically inactive. Why optically inactive? Because if it is clockwise rotation is there, obviously it will be anti-clockwise rotation, the resultant will get cancelled. So due to internal compensation, internal compensation, internal compensation, just before I told you in case of racemic mixture, due to external compensation, that is optically inactive, but here due to internal compensation it is optically inactive. Of course chiral carbons are there. See here, this is the chiral carbon. chiral carbon here, one chiral carbon is the two chiral carbons. All four different groups are there, even though optically inactive. Why? Because internal compensation, this compound is optically inactive. You can see next example also. Now, okay, this remaining symmetries we can discuss in the part 2.